So this is a hike I'm super excited about. Double check that you're on mute for me real quick. I'm getting a little feedback from somebody. Okay, this hike is here in Arkansas, and it's actually right up around the Ponca area, which is, if anybody's been floating the Buffalo before, Buffalo Outdoor Center, there's so many good hikes in that area. So this one is actually, you start it at a campground. Anybody heard of Kyle's Landing before? Kyle's Landing Campground. It's right there on the Buffalo River. It's a very popular spot to like put into the river or get out of the river if you've been floating. And anyways, this is called Eye of the Needle. This trail is, or it's also called Indian Trail, Eye of the Needle Indian Trail. Kind of has two names, but it's got this cave. It's got a couple waterfalls. So this cave they call Arkansas Cave. Can you see why? It's kind of like an inverted Arkansas. And anyways, there's this really cool waterfall, and you don't get to hike back into the cave. That would be really cool, I know, but it's on the other side. I took this kind of across from a little ravine, so you can take pictures of it, but I don't think you can do any hiking in it. And then there, if you look directly, if you're looking at this cave and the waterfall, and then you turn and look directly to your right, you see another waterfall. That's right there. It's pretty fun as well. And then kind of this little steep side that I made my husband stand on, you're gonna climb up that part. And the trail at this point, right after these two waterfalls, gets kind of tricky. Like if you have a dog, if you want to take a dog with you, I don't know if everybody's dog could do like what's next. Because you have to use like some ropes that they have there and kind of climb up. It's not impossible, it's just pretty vertical. And then eventually you get to the grand finale. And so it's this huge rock structure. It's a down and back kind of trail, not like a round loop. And so this is like the point you hike to, and then you turn around and you hike back. But you can see why it's called Eye of the Needle, right? So really, really cool. If you're wondering how big this is, it's huge. And so it's massive. It's really big. Here's me down at the bottom. And so it's really, really big. Okay. So anyways, it is probably our favorite hiking trail in Arkansas so far. We've not done every one there is to do, but this one is just amazing. The hike there is really beautiful. You think you're gonna get lost. You're like, are we even on the right track anymore? But then so Indian Creek is what it's called, or Eye of the Needle. But then you get to this spot and it's really awesome. I would say definitely take a lunch. It's an all day kind of thing. So don't plan to like do it in the morning and then, fill up the rest of your day. It's going to take most of your day. So, and then you could turn it into a fun camping trip too, if you wanted to just stay and camp at the campground. But anyways, that is my hiking story for the day. But chapter 6, we are past the halfway point, guys. We concluded chapter 5. We're over halfway done. This is probably blowing your mind. It's blowing my mind how fast things are going. On that note, if you guys ever feel like I'm moving too fast, I had a Zoom with a student the other day. It was very helpful. It was a very good Zoom. But they said something that I thought, you know what, I bet a lot of students maybe think this or feel this. It's probably intimidating to type in a chat sometimes on a Zoom when you've got like 40 or 50 people there. I know it's intimidating in a large class to ever speak up. That's always a thing with students, and I remember being that way too. But please, just know if you have a question, I guarantee you 10, 15, 20 other people might have the same question. And as a class, it's very helpful collectively when students do speak up. As a class, other people appreciate them. They never tell you, thank you for asking that question on the chat, or thank you for saying, hey, can you slow down? But please know this is a totally safe environment to do that. And I am asking you to do that if you have questions. So it's not a nuisance to me. I want you guys to give me feedback. And it's been really hard for me to gauge so far in the course sometimes how things are going or how they come across when there's little feedback but anyways. So, okay, that's that. Now chapter 6, moles and mass relationships. So if you've had any sort of a science class or especially a chemistry class before, you may have heard of the word moles. But if you've not, then this is brand new to you. And this is going to be quite a kind of a mind-boggling thing we're going to talk about today. But the way I want to introduce the idea of a mole is I want to talk about something kind of from a dietetics standpoint. So anybody in here, you're a dietetics major, you're headed that route, or nutrition? Do we got any like nutrition majors? No, none. Anybody? Anybody in that field, in that realm? Okay, well, regardless, we know that our body needs to have we need to eat certain things, right? Like we have recommended things we need to take in for our bodies in diets. And so here's a few things in this picture that I've pointed out. Iodine, iron, vitamin. There's different vitamins, there's different minerals, there's different things we need to have in our diets. If we starve our body of certain things, that's going to be bad. Why? Because our body is constantly running millions of reactions every day to keep us alive. Okay. And the sum total of those reactions is called our metabolism. All right. Some of you grew up being like, I just have a really slow metabolism. Some of you like, I have a really fast metabolism. And that's true. Different people have different proclivities with different kinds of metabolism. But how do we know what we need to feed our body so that it can do the things it needs to do? And if we do starve our body of a certain nutrient, there's bad side effects that can happen. So for example, let's talk about iron. A good source of iron, if you didn't know, is almonds. Or sorry, I'm saying iron, iodine. Iron's right down here. Iodine. Okay, so iodine, what is important? Why do we need iodine? Anybody know why we need iodine in our bodies? You guys
Um,
remember? Oh, go ahead.
I was gonna say I don't really know, but like I'm gonna guess that is to balance everything else out. Right?
Balance, yeah, everything definitely works together in a balance. So that's not wrong, Glenn, but I think we can be a little more specific. You guys remember when we talked about
Is it?
isotopes? Somebody was going to say something.
I think that it's like a hormone thing. Like, I think there's a hormone that uses mainly iodine. I think it's parathyroid or some sort of
The
thyroid hormone.
thyroid. That's exactly right, Bailey. Your thyroid needs iodine. Remember when we talked about isotopes? We talked about iodine 131 treatment with your thyroid when people have thyroid cancer. Iodine is really important for your thyroid. So you're going to have major thyroid issues if you do not take in appropriate amounts of iodine over long periods of time. So the recommended amount is that both men and women need 150 micrograms. You guys recognize those units, micrograms a day. Okay, that's not a lot, but it's important to have it. And so there's that one. What about vitamin C? There's tons of sources of vitamin C. I bet you didn't know broccoli was a source of vitamin C. My daughter is a broccoli fiend. I could give her like fried chicken, broccoli, and a muffin on her plate, and she would eat all the broccoli and ask for more before she touched anything else. Okay, I don't know how that happened. But vitamin C is in broccoli, and the recommended amounts there, men need 90 milligrams. So milligrams a lot bigger than micrograms, remember, right? Like 1,000 times bigger. 90 milligrams for men, 75 milligrams for women. Why is vitamin C important? Probably lots of reasons, right? Vitamin C,
I know.
we're still finding functions and uses for vitamin C. Sorry, somebody was going to say something.
I was just gonna say that I know it's like partially for immune support because like whenever you're getting sick, like my mom's always like take vitamin C.
Yes, they have those vitamin Z packs that you can take too. Absolutely, it helps your immune system. And then let's talk about the other one, iron. Okay, obviously, red meat is a good source of iron. There's many other sources for iron that you can go to if you don't eat red meat. And so men need 17 milligrams a day, women 13 milligrams a day. So a little bit less than the amount of vitamin C we needed, but still a decent amount that we need every day. Why is iron important?
You need it for your blood or else you'll be anemic.
Yes, that's right. Iron, we talked about, is an ion that is where oxygen binds to hemoglobin. And then that hemoglobin in our red blood cells distributes oxygen to all of our cells. So if we begin to starve our body of iron, we begin to starve our cells of oxygen. Okay, that's terrible. Don't do that. So, but what's peculiar is that we have learned that the body needs these things, and we've learned that it needs it in certain amounts. Okay. And our body thinks in along the lines of molecules. So we've just finished talking about chemical reactions, and that's more along the lines of how our bodies think and see and process. chemical reactions, things coming together, making the products that we need, or breaking down the food that we give our bodies into helpful tools or building blocks that our bodies can use in other things. But we don't think in terms of molecules all day long, right? We process things differently. So our body, we've determined what our body needs, and we've determined the amounts it needs. And you can see all of these things, all of these units that we've been communicating for these different nutrients are in units of mass. We need a certain amount of micrograms or a certain amount of milligrams. So the body doesn't think exactly that way. It just knows it needs iron. It knows it needs vitamin C. It knows it needs molecules of iodine. Okay. So the question here that I want to pose that we've actually been talking about, how do we know how much nutrients our body needs? I've actually talked about that. So I'm actually going to move right down here. Our bodies see and process molecules. Okay, molecules and chemical reactions. But we don't think that way. We don't communicate that way. We buy, I mean, all throughout our communities, all throughout our lives and such, we buy, sell, cook, work with units of mass. Okay, so for example, if you go to the grocery store and you're going to buy a bag of rice, you don't go buy a bag of rice because it has 1 million rice grains in it, because you don't think along how many rice grains you need. You think you find a recipe that needs rice and you're like, oh, I'm going to need 2 cups of rice, right? Or 4 cups of rice. So you go buy a bag that's a 1 pound or a 2 pound or a 5 pound bag of rice. Same idea with sugar. 10-pound bag of sugar, right? There's an example at the store. I'm going to use black. 10-pound bag of sugar. Okay, we don't purchase sugar based on how many sugar crystals we need, because that's just so small. And we don't buy sugar or anything based on how many molecules of that nutrient or that molecule that we need. Another example here. This is ethyl chloride. Okay, if you can read, it's kind of blurry, but it's a topical anesthetic. So my sports medicine people, why would a topical anesthetic be important? Any sports medicine people? Anybody in that route? Physical therapy? Okay, so if you have an injury or a wound, if an athlete gets injured, and especially if it's an open wound, or I don't know if you'd spray this right on open wound, but topical anesthetics are important. I literally had an ulcer the other day. And so guess what I wouldn't buy? An oral anesthetic, right? We use these in all kinds of ways, but we don't buy them based on how many molecules are in the can. The reading on it is how many fluid ounces is in the can, right? And these are units of mass. Ounces is a unit of mass. So basically, the way the mole, going back to the mole, chapter 6 is all about the mole. This idea of a mole, it's going to help us relate a certain number of molecules to a more useful unit of mass. Okay, mass is useful for us. Molecules is how the body processes. So we've got to find a way to relate these things, mass and molecules. And that's where the mole comes in. Okay, so the mole was developed to relate number of molecules to mass. Number of molecules to mass. So if we're going to address the mole and we're going to begin to unpack this, we're going to start with this idea of molecular weight. We need to look at an individual molecule and we need to be able to determine how much that molecule weighs. And we can actually do that. Okay, so to do that though, there's 2 things we need. A molecule's, how many molecules are used? A molecule's atomic mass, or I think this is repetitive, sorry, molecular weight. Okay, so to get a molecule's molecular weight, and then how many molecules of a given substance are in a certain mass, all right? We need a molecule's molecular weight, and then how many molecules of that substance are in a certain mass. So what is molecular weight? Well, it's just how much a molecule weighs. It's the sum of the atomic mass of every atom in the molecule. So if you have a molecule of water, you've got 2 hydrogens and you've got an oxygen. You've got to take into account the mass of both of those hydrogens and the oxygen to get the total mass of the molecule overall. And we call this a formula weight for ionic compounds, by the way. All right, remember, ionic compounds and covalent compounds are slightly different. Sometimes we use different wording. So we might say a molecular weight for a covalently bonded molecule or a formula weight for an ionic compound. So going back to this ethyl chloride, this topical anesthetic, the way we make it, by the way, this is ethyl chloride right here, C2H5Cl. And you do that by taking a molecule C2H4, ethylene, and you combine it with HCl, and that chlorine atom switches over, and well, both actually, the hydrogen and the chlorine, and they combine. This is a combination reaction, right? And you get ethylene chloride. So these can be combined to make your topical anesthetic. So let's determine the molecular weight of both our reactants and our product in this reaction, okay? So we're going to calculate the molecular weight. So if you have a calculator, you need that. Grab a calculator if you don't have one sitting by you. Calculate the molecular weight of C2H4. So to do this is very simple. I'm going to show you an example here. We're going to just figure out, okay, what kind of atoms do we have?
Miss Everly,
Yes.
someone needed you to go back up real quick.
Oh, I'm sorry. Thank you. Right here, Glenn.
Yeah.
Is that good? Okay. Sorry, I will keep my eye on the chat. So we got 2 carbons and 4 hydrogens in a molecule of ethylene. So we've got 2 carbons and we've got 4 hydrogens. So we're just going to write that down. How many of each kind of atom do we have? Then we need to get the atomic mass of each atom. How do we get the atomic mass? Where do we go?
On the periodic table.
Yes, so if you have a periodic table as well, you're going to need that. Pull a periodic table out. Do I have one on this lecture? No, I thought I did. Grab a periodic table, because we are going to go to the periodic table. We're going to look at the mass number for each element, right? That's usually at the bottom of each square, right under the chemical symbol. So we're going to multiply these 2 carbons by their atomic mass. How much does an atom of carbon weigh? Remember, atomic mass units are AMU. AMU. So we're talking about AMUs right now. Just how much does an atom of carbon weigh? Okay, thank you, Kylie. 12, it's actually 12.011 if we're being real specific, if you're using decimals there. Okay, so 12.011 AMUs. That's how much a carbon atom weighs. And we got 2 of them. So we're going to do 2 times 12.011, and you get 24.022. And then hydrogen. We've got 4 hydrogens. So how much does a hydrogen weigh? Thank you, Brooklyn. 1.008. So do all of that, and you should get 4.032.
Wait, Dr. Everly, so like, how did you get the like atomic mass number? You said it's in the book. You said
Periodic table.
periodic table.
So if you're looking at a periodic table, let me scroll and see. I know I have one actually right over here. It's probably right up here. Right here. If you're looking at a periodic table, we looked at carbon. And on carbon, it shows 12.011. That's how much a carbon atom weighs. And then Brooklyn went over to hydrogen, and she rounded 1.008. Okay, so we're just pulling these masses directly off the periodic table.
Okay.
Great question, Glenn. Okay, and now we're just going to add that up. We've got the individual total amount of the elements, and now we're going to combine that all together to get the mass of the molecule overall. So you're going to add these things, and you should get 28.054. And that is the molecular weight of ethylene, C2H4.
So like, would you still write like 4 hydrogens, or like, can you just write hydrogen, or do you have to be like specific?
You need to take into account how many you have, right? If you just had 1 hydrogen, that's going to give you a different mass than if you have 4 hydrogens. So you have to multiply it by the number of that particular atom in the molecule.
Okay.
So now let's go to HCl. We've got hydrogen and chlorine. So go ahead and calculate the molecular mass, or the molecular weight, of hydrogen chloride. You got 1 hydrogen and 1 chlorine. Oops. Okay, and then times for chlorine, I'll jump over to that periodic table again. 35.4, we'll just say 0.45, 35.45. Okay, and then you're just going to add those up. Okay. So that's the molecular mass. That's how much 1 molecule of hydrochloric acid, hydrogen chloride weighs. And then lastly, the most complicated one is C2H5Cl.
On like an exam, if we put like the exact number that's on the periodic table, will it like have a buffer on there? Like, because I got 36.4607 because I used the exact numbers.
Yeah, so on Blackboard, if I were to have you type your answer in, I would probably have this answer, and then I would say plus or minus like 0.5.
Okay.
Yeah. Because there's just no way everybody's going to get the exact same answer to like 3 decimal places. Even if you all use the same periodic table with the same numbers, I promise you people would get different answers. That's just how it is. So yes, great question, Tori. Okay, so now the last one, we've got 2 carbons, we've got 5 hydrogens, and we've got 1 chlorine molecule. So you're just going to multiply these. We've already got all the numbers from the previous problem. So 12.011 AMUs for carbon, 1.008 AMUs for hydrogen, and the 35.45 AMUs for the chlorine. Oop, 2. Okay, is this what you guys got? And then you add them all up. What did y'all get? Anybody have the total already?
64.522.
64.522. All right, so this is how much 1 molecule of the anesthetic, the ethylene chloride, weighs. Okay, so do you guys feel comfortable with calculating molecular weight? And now remember, the only time this could get even more complicated is when you have like parentheses. Let's say you had like Al2CO3 3. You just would have to remember that there's not just 1 carbon and 3 oxygens in aluminum carbonate. There's 3 carbons and 9 oxygens, right? When you calculate things like that, okay? So I didn't do an example with the parentheses here, but remember this 3 multiplies everything in that parentheses, the carbons and the oxygens, by 3. If you're calculating the mass of a molecule that has parentheses. So, okay, here's a summary of everything we just did in a table. All right. Now we started talking in this lecture about how our body sees molecules. We work in terms of mass. So AMU is just a really small unit though, right? It's relating to things so small. It's a unit we made up to talk about things that are small. Oh, Whitney said, can you scroll up so I can see the original problem? Whitney?
Never mind. It's okay. It's right there. I'm sorry.
Oh, you're good. You're good. Okay. AMU is too small of a unit. That's the point I want to make. We don't use terms of AMUs when we're talking to each other or when we're. Sorry, somebody's like laying on their horn outside. Did y'all hear that? Oh gosh. Okay, AMU is too small of a unit. So because of that, we have to use a different unit. Okay, a unit that is way more functional for us is a unit of grams. Okay, we can understand how much a gram weighs. Our minds can't even comprehend how much 1 AMU is. It's just so small. Remember that 1 never mind. I'm not going to get to that. We talked about AMUs in chapter 2, and we looked at the actual mass of like a proton and a neutron in grams. And then we just said, a proton's 1 AMU, a neutron's 1 AMU because their mass in grams is so small. But we're going to go back to grams now. And so there's something that's very cool that happens if we just mark these units out and replace it with grams. So now instead of 28.062 AMUs, if we have 28.062 grams of ethylene, and then you apply that to all the other molecules as well, there's something really cool that happens. And it's down here in red, I'm gonna read this. When a substance weighs numerically the same in grams as its molecular weight, the number of molecules present is now called a mole. And we abbreviate it MOL. I'm gonna read that again. When you have the same amount of a substance in grams, when a substance weighs numerically the same in grams as its molecular weight, then the number of molecules present to make up that mass is a mole of molecules. Okay, a mole of molecules. Everybody say a mole of molecules. Nobody's saying it. You could also have a mole of atoms, okay? I want you to understand the word mole much like we understand the word dozen, okay? A dozen just stands for a number of items, right? We commonly think of eggs, right? Because that's how they're sold, in a dozen. But you could have other things in a dozen, right? You could have a dozen people. You could have a dozen houses. You could have a dozen pencils or a dozen, whatever. A dozen just stands for a number. And what number does a dozen stand for?
12.
12, okay? It's the exact same idea with the mole. A mole just stands for a number of something. And it's a very, very large, astronomically big number. But it just works the same way as a dozen, okay? So remember that as we go on. So, okay, we're gonna fill out this table. So we're talking about the same reaction here, this ethylene chloride reaction. And when we have the same molecular weight as we do in grams, so when we have 28.062 grams.
Sorry, Dr. Beverly, can you go just like a second? Like I was on like the last 10 minutes.
Uh-huh.
Okay.
Good deal. So 64.522 grams. So when we have this amount of each substance in grams, how many moles do we have? We have 1 mole, okay, 1 mole of each of those molecules. And I bet you're wondering, okay, well, what's the number? How many molecules do we have? And I'll tell you that in just a second. Okay, and then how many molecules is present? So that's what we're gonna get to. Anybody actually know the number of items or molecules that is in a mole? It's got a name. It's such a big number that we've named that number. And it's called Avogadro's number, okay? Anybody know what that number is?
They're like 6 point something.
It is. Are you Googling it right now?
No, this my chemistry teacher in high school.
Uh-huh.
was saying
Okay,
something
Blake
about
got us halfway there at 6 point something. Okay, Rachel got us further, 6.022 something. Okay, and then Brooklyn, there we go. 6.022 times 10 to the power of 23. She said maybe, but Molly confidently says 6.0. Oh, 6.022, Molly, very, very close. Times 10 to the power of 23. So this is the number of molecules in a mole, all right? And if you want the actual definition of a mole right here, it's the amount or quantity of a substance whose mass in grams is numerically equal to its molecular weight, okay? It's the quantity. It stands for a number of items. The quantity of a substance whose mass in grams is numerically equal to its molecular weight. So if we have 1 mole of a substance, question?
Okay, that's just like weird to me because like they're all different like weights, but they're all 1 mole.
Mhm.
So moles are like relevant to the molecule then, right?
Moles just stand for a number of items. So let me fill this in and maybe this will help, Bailey. 6.022 times 10 to the 23. Y'all are gonna like what I'm about to do. Copy. You wish you could do this on your paper, I know. Can I do it? Will it let me paste? Usually I can. Maybe I didn't copy it. Okay, now it just looks stupid. Okay, it won't let me. I'm just gonna write it like a normal person. I thought I was gonna do something cool. So Bailey, going back to your question. Yes, it is kind of confusing. I don't want you to think it does have to do with the molecular mass of a molecule, okay? Because that part relating the AMUs to the grams and that being numerically equal, we've made a big deal out of that, right? But a mole, again, it just stands for an item. So just the way a mole could stand for 12 pennies versus 12 cars. Obviously, a penny and a car don't weigh the same thing, right? A penny is a lot lighter than a car. A car weighs tons and tons, and a penny is very light. It's the same idea here. We could have different molecules that weigh different things. You can have a hydrogen molecule that weighs very, very little. And then you could have a molecule of sucrose that weighs a whole bunch. But it's not about their weight necessarily. A mole stands for how many molecules of hydrogen or how many molecules of sucrose are present. Okay, and it's the same number across the board. When we have 6.022 times 10 to the power of 23 molecules, we have a mole of that substance. Now think about, this is useful to us, and it has to be this astronomical number because molecules are so small we can't even see them. Okay, so if we're going to deal with molecules in the lab or in the kitchen when we're cooking or in society in general, if we're going to buy a 10-pound bag of sugar, if we're going to buy things from the store in useful amounts, it has to be astronomically huge numbers of molecules, right? So that's why that number makes sense. It's just, it is a very, very large number. How big actually is it? Let's look at this. This slide makes me laugh because I like to put in my own markers along this line. So this is Avogadro's number. And if you write out all the zeros, there they are, okay? And if you start way down here, so this is obviously the ones place, the tens place, hundreds, thousands. This is the tens of thousands place. I thought this was funny. It says the average college tuition. And I always say AKA average student loan debt, right? It's actually very depressing. You can go to a website and type in national student loan debt, or you could probably even do a global scale. And it's just a number that's literally scrolling continuously upwards. Isn't that scary? Okay, so average student loan debt. And then we can continue going up until we get to the billions place. And this is the population of the earth, right? That's always continuously climbing as well. And then you can keep going and keep going and keep going. Last semester, right after the presidential debates, anybody watch those? I said we got the age of the earth and the distance from the earth to the sun, but even above that, we have the national. Oh, sorry, I think it was even bigger than that. It was the global number of eye rolls from the presidential debate. Did you guys watch those? I rolled my eyes a few times. That's all I'm going to say. So it's a huge number. Okay, it's even bigger than that. So Avogadro's number is massive, and it's hard for us to comprehend how big it is. But when we have that number of molecules present, we have a mole of molecules. Okay, so let's go back to this table. We're going to begin, now that we know what a mole is and what it relates, we're going to start to use it as a conversion factor, okay? As a conversion factor. And remember, a conversion factor is something that just relates 2 units. And so here, we can use molar mass as a conversion factor because it is a relationship between the number of moles and mass, okay? Number of moles and mass. Same idea the way we use density. Density relates mass and volume, right? Moles relates moles and mass. So we used to use density to convert. If we said, oh, here's the density of a substance and I have 10 grams, what's my volume going to be? We use density to convert between that. Same idea with the moles. If I tell you I have 3.5 moles of something and I want to know what's the mass of that something, well, as long as I know what the substance is, I can calculate how much that'll weigh in grams. All right. And we're going to use molar mass to do that. So because we can relate these two things for any substance. We can figure out what the molecular weight is and write units of grams, and we know that's 1 mole of a substance. Okay, so we can convert that for any substance. So we're going to do some practice problems in a minute. All right, and so molar mass, just I wanted to write one thing here. You could write it like this: the number of grams per 1 mole. Okay, number of grams of a substance per 1 mole. And then you can see how we're going to begin to use that to convert. All right. So that's molar mass. And then Avogadro's number is also a relationship we can use to convert. Okay. It's a conversion factor between the number, between moles and number of molecules. So I'm going to shrink this down actually. Avogadro's number, I'm just going to write A in. This is often the way you'll see it abbreviated, Avogadro's number, A with a small n. This relates, we can use it to do number of molecules per 1 mole. All right, so we can use it to relate between moles and number of molecules. All right, so let's start doing some of this. So you're gonna need a calculator. The very first question I want to ask you is, what is the mass if we have 6.022 times 10 to the power of 23 carbon atoms, which is 1 mole of carbon atoms? What's the mass of that? How much will that weigh? So we know for carbon, if we have 1 mole of carbon atoms, well, we know this. We know 1 carbon atom weighs how much? If you just flip over to the periodic table and you look directly at it, we saw that number earlier was 12.011. In the chat, Glenn says, what is the AN number again? I can scroll back up at that in just a second, Glenn, hold on. I'm gonna grab this number though, 12.01. That's how much 1 carbon atom weighs. Okay, and here we're not talking about a molecule, we're just talking about an atom of carbon. And so if we cancel that out and turn it to units of grams, we know this equals 1 mole of carbon atoms, right? There you go, Glenn. Maybe you can see it up top now. All right, so the question, what is the mass of 6.022 times 10 to the 23 carbon atoms? Well, that's 1 mole, and it just weighs 12.011 grams. So I want to point out, if I'm just dealing with an element and not a molecule, you actually don't have to calculate anything. If I ask you what's the mole or what's the mass of 1 mole of aluminum, what's the mass of 1 mole of oxygen, what's the mass of 1 mole of sulfur, you literally just go to the periodic table, you look at the mass number, and you say, oh, it's that many grams. Okay, does that make sense? You have to, the only time you have to calculate something is when you have a molecule and you have more than one kind of atom. All right. Now, if I said, what's the mass of a molecule of oxygen? Because we know oxygen exists as a diatomic molecule, right? It's O2. So that is, we can't just, if I say a molecule of oxygen, even though it's just one individual element, we still have to multiply the mass of an oxygen atom by 2. Does that make sense? We have 2 oxygen atoms. And by the way, I do want to point this out. When we're talking specifically about oxygen, look at oxygen, 15.9994. Just use 16. Just use 16.0, okay? Because you're going to round anyways. 16.0 is way easier, 16.0. So if we're talking about a molecule of oxygen, just multiply that by 2 and it's 32 grams. That equals 1 mole of oxygen, molecular oxygen. So, okay, now we're going to work a problem that has a little more depth to it. Oh, yes?
The diatomics, 1 mole is equal to 2 of them and not 1
Yes.
in every single one of them.
So this goes for like fluorine, because that's a diatomic. Nitrogen, you go to the periodic table, get the mass, multiply it by 2. Because you have 2 atoms in a molecule of fluorine or nitrogen or hydrogen or any of the diatomics. Okay. But if yeah. All right, let's do this problem. Okay, the chemical formula for aspirin. All right, aspirin's a pain reliever. It's C9H8O4. C9H8O. You got 9 carbon atoms, 8 hydrogen atoms, 4 oxygen. How many molecules are in 25 milligrams of aspirin? Okay, I read that problem really quick. Let's break that down. How many molecules are in 25 milligrams of aspirin? I'm going to draw a little diagram that I want you to write down that I think should be helpful. So moles is always the middleman between number of molecules and mass. Okay, so if we start out with mass, okay, like this problem gives us a mass. Milligrams is a unit of mass. To convert to number of molecules, we first have to convert to moles, and then we will convert to number of molecules. Now, to do each of these steps, to convert from mass to moles, what did we say our conversion factor was? What is a conversion factor that relates mass and moles? Let me go back up, right? Molar mass. Molar mass is the conversion factor. Sorry, someone was about to say and I cut you off. Okay, so we're going to use the molar mass. That's going to be step 1 to convert from mass to moles. Now remember though, molar mass is in grams. This relates gram per mole. Right now we have milligrams, so we have a step even prior to this. For this particular problem we have to do. We've got to first convert milligrams to grams, then we'll use the molar mass. Then we're going to use Avogadro's number to convert from moles to number of molecules. All right, so that will be step number 2. This is actually going to be a 3-step problem because we first have to convert milligrams to grams. So let's do that. We've got 25 milligrams. Let's convert that to grams. Do you guys remember how to do that? How many milligrams are in a gram?
1,000.
Okay, good job. Now we need to plug in the molar mass. Do we know what the molar mass is? Well, we need to calculate it. So let's calculate the molar mass of C9H8O4. I'm going to really zoom in small. We got 9 carbons, we got 8 hydrogens, we got 4 oxygens. And I'm going to use units of grams here. You don't have to write the AMUs this time because we want molar mass, which is grams per mole. So same numbers from the periodic table, but units of grams. And remember for oxygen, instead of using 15.999999, just use 16. Okay, so this should be, anybody want to add?
So AMU and grams are interchangeable then, right?
Well, when you are calculating if you're calculating a molecular weight, like the weight of one molecule, Bailey, then you're just using AMUs. If I ask you to calculate a molar mass, you're calculating the mass of an entire mole of substance, So then you're using grams. Okay, so maybe make a note of that. Molecular weight is AMUs. Molar mass is grams. So here we're calculating the molar mass of aspirin so that we can convert from grams of aspirin to moles of aspirin. But if I ask you what is the molecular weight of one molecule of aspirin, you could use AMUs. Okay, anybody have the total for us? What is 9 times 12.011? 90, what is 18,108? Is it that?
Yeah.
Okay, and then 8.06, no, 8 times 8 is
4. Yeah.
and then 4 times 16 is 64. Okay, and then Brooklyn
Well,
got,
somebody got a 9, a 6, like the first one. Like
I
the same.
think that's, oh, is it 9.6?
I got 9.9.
Brooklyn, what is 108.96? Was that what you got for carbon or the whole?
That should be like
Carbon, okay. Well, just slightly off. That's all right. All right, then you sum all of these up, right? So then we got 16, is it 180
Yeah.
point? This is old school math right here. We got a 3 and then carry the 1 and then is that it?
Yeah.
Okay. 180.163 grams of aspirin in 1 mole of aspirin. Okay, so what this means is we have 180.163 grams of aspirin equals 1 mole of aspirin. That's what that means. That's the molar mass. So now we have converted from milligrams to grams. We cancel, I meant to do that in black. Cancel milligrams and converted to grams. So now we want to go from grams to moles. So we're going to plug this in. So we got 180.163 grams for 1 mole of aspirin. Okay, and I just plugged in my molar mass. So that was step 1 that I just did. So I've now converted from mass to moles. Now I want to, the question says how many molecules. So now we want to use Avogadro's number. Well, we know that 1 mole, I want moles to cancel, is 6.022 times 10 to the 23 molecules of aspirin. And when you're dealing with Avogadro's number, especially when here we're multiplying by Avogadro's number because it's on top. If you're dividing by Avogadro's number, make a note of this. Put it in parentheses. If you have to divide by Avogadro's number and it's like on the bottom somewhere under one of your conversion lines, put it in parentheses. Okay, because if not, your calculator will only divide by 6.022 and it'll actually multiply by 10 to the power of 23 and you'll get way the wrong answer. Okay, anybody have our answer? Do 25 divided by 1,000 divided by 180 times Avogadro's number. What do we get? You're going to need a real calculator. I don't suggest using your cell phone. Okay, because cell phones sometimes is just hard when you're dealing with really, really big numbers and exponents. Anybody have our answer for us? Okay, Chris said 8.3, we'll round, 36 times 10 to the 19. And this would be molecules of aspirin, all right? So if a problem asks you for a number of molecules, usually that's going to be a very large number, okay? Here we've got times 10 to the power of 19. Questions on what we just did? That was a pretty in-depth problem.
I have a question. Like when you get to like actually doing the work, my teacher always made us do like what like the number in the question is, like that's how many places we rounded to. So like we had 25, so we only did 2 places. Is that how you want us to do, or do you want it like 3 every time?
I generally like 2 decimal places, and usually you'll see on like an exam, I'll tell you, include 2 decimal places or include 3 decimal places or no decimal places. So I'll make sure to give specific directives on how to type your answer in if it matters. Like when we're working it in lecture, usually 1 or 2 or 3 decimal places, I'm not going to be picky. On the exam, I understand that Blackboard is more specific. So I'll tell you, and like you'll see on the lab that we're going to do today, tomorrow, and Monday, that there's a lot of specific instructions. So no sig figs. Yeah, Molly, we haven't even talked about sig figs in this class. I'm not saying they're not important, but we just have way more stuff to cover than to learn all the rules of sig figs. Okay. I know sometimes on Mastering Chemistry, it tells you only put your answer into 2 significant figures. So, but I have no control over how they word their questions. So sorry for that. But yeah, does that help at all, Brooklyn? on when we're working it in lecture, I'm really not going to be picky. Okay, so now I want to do I want you to attempt this problem on your own sometime. I want to skip over this and work another one. And then we really are kind of only got about 25 minutes of class left. So I really want to get to a few other things, but let's work another problem. Let's go down here to the one about water. So how many moles are in 60 grams of water? How many moles are in 60 grams of water? So here we have mass and we're trying to convert to moles. Okay, anytime you're converting mass to moles or backwards, moles to mass, you're going to use molar mass. We need to calculate the molar mass of water. What is water? We need the chemical formula for water. We know that is H2O. So this is going to be a one-step thing. First, we need to get the molar mass of water. Then we'll use the molar mass and convert 60 grams to number of moles. So in water, we've got 2 hydrogens. Remember, we're working with molar mass, so we're going to use units of grams. We've got 1 oxygen, and we're just going to use 16 for that. Grams is in 1 mole of water. Okay, so this is our molar mass, 18.016 grams per mole. All right, so start with the number given, 60.0 grams of water. Now we're going to cancel grams and convert to moles. Cancel grams, convert to moles. So I want you to plug this in so that grams cancel, plug in your molar mass, and then you get moles on top. So 60.0 divided by 18.016. And you should notice that grams cancel. Kylie says 3.33 moles of water. Okay. And then if I even ask you, how many molecules of water is this? You could convert, right? You could take this number of moles, use Avogadro's number, and convert to number of molecules. We're not going to do that here, but you could. All right. This is the reverse of the problem above. Up here, we were asking how many moles. Now we are given a number of moles, and we want to know how many grams this is. So I want to prove to you can work it backwards. We just need the molar mass of iron. So we have moles, and this time we're converting the opposite way. We want to go to grams, mass. If I ask you how many milligrams or kilograms, you'd first go to grams, and then you would just convert to milligrams or kilograms, no problem, right? So we still need to do a one-step conversion using molar mass. So what is the molar mass of iron? This one's actually easy. We don't even have to calculate it. What do? We just go to the periodic table. Iron is Fe right here. So we're going to use 55.847. 55.847. So start with 60, or sorry, it's 0.60 moles of iron, Fe. And we said, I already forgot the number. What was it? 55.847. So for every 1 mole, I want moles to cancel this time. So I plug in mole on the bottom, and I know that 1 mole of iron is 55.847 grams of iron in 1 mole. This is our molar mass that we're plugging in. And moles cancel, and then you have grams. So 0.6, so a little over half of 55. Is it around 30? 32? 33.51. Okay, does that make sense? All right. So that is the mole. that is molar mass. That's how to convert between mass and moles. And we've even used Avogadro's number on the one with aspirin. Here's another practice problem. I'm gonna put a pin in this and save it for later. We might do this on some review, okay? But there's an extra practice problem from the lecture notes. Because we're running tight on time, I'd love to work this, but maybe I can do this on a little review day or something before the exam. So I'll come back to that. All right, I really need to get to mole ratios, and I really need to get to, what else do we have? Well, mole ratios. I need to get to mole ratios before the day's up, so I don't want to rush it. All right, so we're gonna start right here. So mole ratio, what is a mole ratio? Well, remember, we just finished a whole chapter on chemical reactions. So if we have this chemical reaction right here, hydrogen plus nitrogen makes NH3. NH3 is ammonia. Ammonia is a really powerful molecule. We use it in a lot of things, fertilizers, all kinds of stuff. We use it for energy. Hydrogen reacts with nitrogen to make nitrogen trihydride ammonia. So if we're gonna balance this equation real quick, because it's not balanced, let's do that. What do we need to do? What coefficients do we need to plug in to balance this?
I would first put 2 in front of the nitrogen trihydride and a 3 in front of the hydrogen.
3 and 2. Okay, then we got 6 hydrogens on each side. 3, 1, 2, yeah. So there'll just be understood 1 right here. Okay, good, I like that. So now it's balanced, and we got 2 nitrogens on each side. Good. So based on these coefficients, I want to read these little color-coded phrases. What these coefficients tell us is a ratio between our reactants and products. And it's a ratio of moles, okay? We haven't written moles in, but we easily could. We could say 3 moles of hydrogen reacts with 1 mole of nitrogen, and it's going to yield 2 moles of ammonia. You could easily write units of moles in, okay? That's what these color-coded statements are saying. This number of moles of hydrogen, 3 moles of hydrogen, reacts with this number of moles of nitrogen, 1 mole of nitrogen, and every time we do that, we're going to get 2 moles of ammonia. Okay, you see how it's, remember when we related chemical reactions to a recipe? And that's what we said, coefficients help us know how many of each ingredient and how much of our product. Here, we're just applying units to that. We're saying it's a ratio of moles. So we can use mole to mole ratios to convert easily between our reactants and our products. So what is a mole ratio? From what we just said, we can write little conversion factors. For every 3 moles of hydrogen, I know I'm going to get 2 moles of NH3, that much of my product, if I have 1 mole of nitrogen, okay? So this would be a mole to mole ratio between hydrogen and ammonia, one reactant and the product. We could write another mole to mole ratio between our other reactant and the product, between nitrogen. And then let's do that. For every 1 mole of nitrogen that we put in, we're going to get 2 moles of ammonia. So for the hydrogen and ammonia, the first one we wrote, we would say it's a 3 to 2 mole to mole ratio, 3 to 2, when we're just looking at the coefficients there, right? For nitrogen and ammonia, we say it's a 1 to 2 mole to mole ratio. So this is the mole to mole ratio between nitrogen and ammonia. We could even write a mole to mole ratio between our 2 reactants. Write a mole to mole ratio between, it does not matter which one you put on top and which one you put on bottom. You could flip these, okay? You could have ammonia on top and the reactant on the bottom. But if you write one for the 2 reactants, you'd say for every 3 moles of hydrogen, we need 1 mole of nitrogen. So there's a 3 to 1 mole to mole ratio between hydrogen and nitrogen. Okay, so that's what a mole to mole ratio is. You're just looking at the coefficients, but the equation has to be balanced. To get the mole to mole ratios right, you have to balance it right. Okay, questions on this? What questions do y'all have? Okay, so just the same way, if I said, okay, I want to work actually a little problem now. I'm going to erase this. I'm going to make up my own problem. If based on this equation with ammonia, if I have 10 moles of hydrogen, if I have 10 moles of hydrogen, how many moles of my product can I get? I want you to convert that. If I have 10 moles of hydrogen, how many moles of ammonia can I get? Let's say I have plenty of nitrogen. I'm not worried about my nitrogen here. But if I only have 10 moles of hydrogen, what's my max amount of a product that I could get? How many moles? What should I do? Remember, these are conversion factors. You need to pick the one that allows you to convert between moles of hydrogen to moles of ammonia, NH3. And I want to cancel moles of hydrogen. So I want to multiply it by this first conversion factor, but I'm actually going to flip it over because I want moles of hydrogen on bottom. So I'm going to write for every 3 moles of hydrogen, H2, so I just plugged in the top part, I'm going to get 2, you see how I just flipped it? 2 moles of NH3. And moles of hydrogen will cancel out, and I will be left with moles of ammonia. So if I have 10, how many moles of ammonia? Well, you're going to do 10 times 2, which is 20, divided by 3. What is that? Should be like 6 point something. 6.67. Okay. So what you just did is you did a mole to mole ratio, and you converted from moles of your reactant to moles of your product, okay? So that's what these figures are getting at. When you need to convert between moles of one thing to moles of something else, you can use a mole to mole ratio for any reactant or any product in the reaction as long as it is balanced. Okay, so a mole ratio allows you to convert between moles of substance A to moles of substance B. That is different from a molar mass, right? We've been using molar mass to convert from moles of something to grams of something. Okay, this is units of grams. Here, we're using units of moles the whole time. So molar mass is always grams per mole. How many grams of that substance is in 1 mole? Now, if you have a chemical reaction, okay, A plus B makes C. And I say, I got 50 grams of reactant A. How many grams of reactant B am I going to need? So if I have mass of A, which is units of grams, so let's say I got 50 grams of substance A, I want to know how many grams of substance B. We actually have to use both. Both what? Both a mole ratio and molar mass. These are the most complicated parts. These are the most complicated problems, okay? If you have a mass to mass conversion that you have to do, so mass grams of A to grams of B, this is how you work it. It's this downward little diagram here. You're going to start with the mass of A, okay? We're given 50 grams of A. The first thing you have to do is you have to convert that mass of A to moles of A. Well, how do we go from mass to moles? Look at the diagram. We can convert moles and mass using molar mass. So you're going to use the molar mass of substance A. That's step number 1. This is a 3-step problem. These are always 3-step problems. Step number 2, how do we go from moles of A to moles of B? Oh, that's easy. That's our mole ratio. Okay, each individual step is not the difficult part. It's the sum of putting it all in order. That's the hard part. Okay, so then you're just going to use a mole ratio between A and B. And you look at your balance reaction for that. Now that you have moles of substance B, when you're all said and done with steps 1 and 2, you have moles of substance B. How do you convert to mass of B? Well, I know this says A and A over here, but you can really apply it to any substance. It could be moles of B to mass of B, all right? So now you're just going to use the molar mass of substance B. And that is step 3. This is very scary because how we remember what order when you give us problems. I don't understand why the order is the way it is. Bailey, you always have this diagram. Remember, your exams are open note. So we're going to do a lot of practice problems with this, and that's going to help you. I don't expect you to be comfortable with this idea right now. Okay, so that is perfectly normal. We're going to do a lot of practice problems so that you can become comfortable with it. And that's what lab is for. Okay, so please don't attempt lab on your own. Please show up to lab. And you and your group mates and me, we're all going to do it together. And we're going to work tons and tons of problems just like this. And you're going to feel so good about it by the time that you're done, if you will put in the time and the effort, that I don't think it will be scary to you anymore. Okay. But the order is the way that it is because of all the foundational steps we've talked to. Oh gosh, oh my. Okay, there they are. Because of all the things we've talked about, because the way mole and mass work together. I don't know if I'm explaining that probably not very well, but there's not a simple answer for why this diagram is the way that it is. It's built on a lot of individual steps, all right? And it's built on an understanding of a mole and how it relates to mass. And then also between a balanced chemical reaction. Hopefully you guys understood this part about relating moles and moles. And then it's all of that combined. That's how we get the diagram in the order that it is, okay? You can't just convert directly from mass of A to mass of B because you're not taking in the ratio for this particular chemical reaction. Every chemical reaction is unique. Every chemical reaction has its own set of coefficients that balance it. So that's why we cannot just go mass of A to mass of B. We have to use a mole to mole ratio in the middle because we're working in the context of this chemical reaction. Okay. All right, so let's break this down. Let's do some steps. All right, we have an example of a chemical reaction here. Iron, when it's oxidized, so iron reacting with oxygen, makes rust. So rust is Fe2O3, iron oxide. And the question here is how many moles of rust are made from 7 moles of iron? How many moles of rust are made from 7 moles of iron? So we have moles of iron, and we want to convert to moles of rust, which is the Fe2O3. So here we have a question, and the units will help you as well, Bailey, going back to your question. We have a mole to mole question, right? We can treat iron as A, and we can treat iron oxide as B. So we're just trying to convert from moles to moles. So we're just going to use a mole ratio. All right, so this question, we're just going to use a mole ratio. So let's write that out. What is our mole to mole ratio between iron and iron oxide? Look at the balanced chemical reaction. It's already balanced for you. You write that out. Our coefficient for iron is 4. Our coefficient for iron oxide is 2. So for every 4 moles of iron, it's 2 moles of Fe2O3. Now, some of you may recognize that you can simplify this, right? You could say 2 and 1. But guess what? You get the same answer whether you simplify or whether you don't. So if you forget to simplify, it's okay. So we're just going to use the non-simplified form because it's not going to mess up our answer. So 70.0 moles of iron. Now I'm going to plug in my mole to mole ratio, convert to moles of rust, Fe2O3. So I want moles of iron to cancel. So I'm actually going to put this part on bottom down here. So for every 4 moles of Fe, I'm going to take this part and put it on top over here. It's 2 moles of Fe2O3. And moles of iron cancel. You got it on top and on bottom. So then you'll do 7 times 2, which is 14. Divide that by 4. What do you get? Anybody have an answer? 7 times 2 divided by 4? Grant got 3.5. Kelly got 4.67. Alex got 3.5. I'm gonna go with 3.5. Is that right? Yep. Okay. All right. I think we got time for one more question. That's all right, Kylie. I think we got time for this one more question. And then you can see I had 2 more practice problems. And then the rest down here was going to be review. And we'll get to that on next Tuesday. Okay, so literally we covered all of chapter 6 in one day. So let's do this last question right here. And then if anybody has further questions, I can stick around and answer those. Okay, this next one says, well, how many moles of rust are made if we have 83 grams of oxygen? So look at your units here. We are given grams, which is mass, and we're going to call whatever your grams are, whatever you're given here, we're going to call it mass of substance A. So we have a mass of substance A, and we are trying to convert to moles of substance, what we're going to call rust substance B. So how do we do that? How do you go from mass of one thing to moles of something else? This is going to be a 2-step problem. First, we have to go from mass to moles of A. That's step number 1. Step number 2 is we're going to use the molar mass of substance A, which is, in this case, oxygen. All right? We're labeling oxygen. Oxygen is substance A, rest is substance B. And then my second step here is I'm going to use a mole ratio between oxygen and rest. Okay? 2-step problem. So first, what is the molar mass of oxygen? My molar mass of oxygen, if we go to the periodic table, one oxygen atom weighs 16 AMUs, or we're going to use units of grams here because we're talking about molar mass. So 2 times 16 is 32.0 grams of oxygen for every 1 mole of oxygen. All right, that is my molar mass, and I'll plug that in for my first step. But then we need the mole-to-mole ratio. Okay, what is the mole-to-mole ratio between oxygen and rest? We look at the balanced chemical reaction, we got a 3 and we got a 2. So for every 3 moles of oxygen, 2 moles of rest. So it's going to be 3 moles of oxygen for every 2 moles of Fe2O3. So we'll plug that in just a second. So let's start. I'll let you guys catch up. All right, we're at 9:15. I got to wrap it up. Let me write this out. 83.0 grams of oxygen. First, we plug in the molar mass of oxygen, which is 32 grams for every 1 mole, right? Because we want grams to cancel. And this is oxygen. I encourage you to write out what substance you're talking about along the way. Now I want to cancel moles of oxygen, so I'm going to come over here, grab my mole-to-mole ratio. I'm going to write moles of oxygen on bottom so that moles of oxygen cancel. So that's 3 moles of oxygen for every 2 moles of Fe2O3. And moles of oxygen cancel, and you get moles of rest. So you do 83 divided by 32. 83 divided by 32, and you do times 2, and then divided by 3. And you should get how many moles of rest are made? 1.7, if you round, it's 1.73 moles. All right, I'm done. Sorry, I went a minute over. Okay, that was a lot. So if you feel a little bit overwhelmed right now, you're probably not the only one. Take a deep breath. We're going to do a lot of practice on this in lab, and you'll be a lot more comfortable with it. Thanks for joining. Don't forget things that are due tomorrow. Print off the PDF, the mole calculations PDF for lab, and show up ready to go with that. Have a calculator ready to go. I'll see some